Hello everyone, and welcome back to another Eng 130 video tutorial. In this week, week 8, we're going to start covering something called internal forces. And these are very important, not so much for this week, but for next week. As you'll see, the stuff that we do this week, which is finding the internal forces at a specific point in a beam, is kind of kind of the first course into finding the internal forces at every point along the beam. And that will be your final exam question. So this week it's a nice introduction. It'll get you used to what internal forces are, how to find them, stuff like that. And then next week we're going to completely escalate it into something a little bit more crazy, and that next week is what will be on your final exam. So for this week, don't really focus on thinking how this will apply to the final. Just kind of sit back, relax, because the only thing that you're really going to have to learn is sign convention. Now when we cut a beam, forces will appear. It makes sense. There's internal forces in the beam, and those internal forces are how the load will transfer in the beam to the supports. Now we're going to calculate those internal forces, but again, like I said, it's going to follow a very specific sign convention. I'm going to show you guys all of that. But if you guys get the sign convention, then this week will actually be easier than trusses last week, because cutting the beam will just result in a couple forces, and we can use our equilibrium to solve for those forces. So it's kind of hard to explain just me talking about it. So let's jump into the example and kind of go over the theory before we get started. So with that said, let's begin. Alrighty, so looking at this example, it would like us to determine the internal forces. So the internal normal force, the internal shear force, and internal moment at point C. So before we get into this is actually kind of a simple question, as you guys will see with one little trick. We got to discuss what internal forces are. And the best way to describe it is what you've already done, and that is trusses. So when we had a truss and we had two members, so let's say we had joint A and we had joint B right here. No matter which method you do, we relied on cutting those members. So let's say our member is this purple thing that goes between these two. And when we're trying to analyze the force in that member, so if we're trying to find out if it's, say, 100 kilonewtons in compression or 300 kilonewtons in tension, what we would do is we'd cut through the member like this. And this applies to the method of joints and the method of sections. And what would happen is our new joints would turn into this. So we'd have two internal forces like this. So when we cut through a truss, we had a single force on each side. So like this. And this right here would be the internal forces in a truss. Just a single axial load in a truss. So I'm going to put this as A and put this as B. And this is for a truss. So trusses were nice and simple because we cut it. We only replace the member with one load. Beams, however, are very different. Very different. And that is if we have a beam. So let's say we have point A and point B. And between these 2 points is a beam. So we got A and we got B. And I'm just going to put right here that this is a beam. What happens to this is we can do the exact same thing as a truss. What we're going to want to do is cut the beam to expose its internal forces. So we're going to do the same thing as a truss. We're going to cut it. But now what's going to happen is when we look at A and B, something special is going to happen. The first is we have to include the distance of the cut, like this. So for the trusses, as you see, once we cut it, we just put two forces on our points. We don't care about the length of those forces or anything like that. But now when we cut the beam, we're going to actually have to care. So what I'm going to do is I'm just going to label this point right here that we cut, point C. And what's going to happen is we're going to have to analyze two things. We're going to have to analyze beam AC. And then there's a second part we're going to have to analyze, which goes like this. And this would be CB. So the two parts of the beam. And we cut right in between them. So let's say that this is distance, let's say 5 meters, blah, blah, blah. Very important. And the reason why is because when we cut the beam at C, so I'm going to erase this because this is kind of in the way. I didn't think I had too far on that one. So I'm going to put C a little bit to the left. But when we cut the beam at C, we get internal forces, just like we do with the truss. The only thing that happened in a truss, though, is we had that one single force. When we cut a beam, we actually have the same force kind of coming out like this. And this is called the normal force. So what I would label this as is N, so normal force at C. So when we look up at the question, it says to determine the internal normal force, that would be that one. However, when you think about beams, beams are very, very stiff. When I had a cable, for instance, and I push down on it, it's not going to really resist anything, it's just going to bend. But a beam is very stiff, it resists that bending. So there's actually another force in a beam called shear force. And this force is perpendicular to the beam. So in this case, what I would do is I'd have a shear force coming like this. So I'd have this one coming down, and shear we usually put as V. So this right here would be VC. And then going back to the stiffness of the beam, what that means is there must be some sort of moment inside of that beam. Because when I press down, the beam doesn't want to bend. It doesn't want to bend at all. So what that means is there's an internal moment holding it up. So another force that we'd have is a moment when we cut the beam. And I just call this MC. So when we cut the beam, we're given 3 internal forces. And that's very, very, very special because remember, for a truss, every member that we cut resulted in 1 force. So we would always say, well, we have 2 equilibrium equations. We can only cut through 2 members or 2 unknown members at a time. But if we look at beams, however, we have 3 unknowns. And we have 3 equilibrium equations. And the third one we can actually use for beams is because we deal with distances. It's not like trusses where everything acts at a point now. We have that distance, therefore we can use sum of the moments. So in a beam, we're going to have those 3 equations. We're going to have sum of the moments equals 0. Sum of the forces in Y equals 0. And then sum of the forces in X is equal to 0. So we can only solve for 3 unknowns. And when we cut the beam, we're given 3 unknowns. So what that tells us is we can only cut the beam at 1 point at a time. If we cut the beam at a second point, well, we're going to have 6 unknowns. Won't be able to solve for anything. But that's okay because we're only usually interested in just a single point anyway. But now, we have to look at the other side of the beam real quick. So at this bottom diagram, where I have C, remember that wherever we cut has to be equal and opposite. If I look at the truss, I cut and I had a force going to the right, while on the other side I had the same force but going to the left. And it is the exact same for trusses. So if I look at C at the top, I have my shear force going downwards. So on this side of the beam, my shear force must be going upwards. Same for the normal force. And that on the top side, I have it going to the right. So on the bottom, it must be going to the left. So this would be NC. So remember, these values would be the exact same across the board, which is very, very nice. And then finally, we also have a bending moment. So we'll have a moment at C. Excuse me. So my voice is still a little bad, but the videos are still going to proceed. So if you hear a little bit of coughing, excuse me. I'm not trying to annoy anybody, but it's just kind of the reality of the situation. I know you guys want these videos just as much as I want to get them out to you guys. So as you guys can see, what's going to happen, it's going to be kind of the same as trusses. We're going to cut a member, and we're going to solve for its forces using equilibrium. It's the exact same thing as trusses. But here's the only thing you guys are going to have to know. The only thing. So I'm going to put a star around it because this is the only thing, and it's very, very important. When we have a beam and we cut it. So I'm just going to draw a random beam like this. So when we have a beam and we cut it, we have those internal forces. Now, the sign convention of those internal forces were basically the way I drew all these arrows up here. That wasn't by coincidence. Remember, for trusses, we always assume tension, and if it's negative, it means it's in compression. Here, we're going to do things a little bit different. And this is called beam sign convention. Beam sign convention. And you guys don't have to remember that because you guys will just always have to use it for beams. And what happens is depending on what side you cut the beam, your forces are always going to act in a certain way. For instance, if I cut the beam right here, and I'm analyzing that cut, my shear force on this side will always be going downwards. And if I look up when I did AC, I see that my shear is going downwards, always. My normal force will always be pointed away from the member, always. So this will be my normal force, this will be my shear force. And finally my moment, so my moment like this, the arrow will always be pointed towards the top of the beam. Always pointed towards the top of the beam. And those normal and moment, they're very, very easy to remember because the arrows are always to one side. So for the normal force, if I were to cut on the opposite side, so now looking at the far side, my normal force always pointed away from the beam. Always. So this will be my normal force. My shear force, this is the only one that gets kind of tricky. My shear force, if I cut on this side, is going to go upwards. So this will be my V. And finally, my moments. For the moment, the arrow is always pointed towards the top of the beam. So this will go like this. And this is the only thing you guys are going to have to really remember are these sign conventions. Because depending on where you cut the beam and what side you want to analyze, you're going to have to replace that cut with these three forces. Now, here's what makes everything very, very, very special. So let's say that I'm analyzing this half of the beam. And I'm trying to find my shear force. And I do something like this. I go, okay, well, shear force is in the y. So I go, sum of the forces in y equals 0. So I write my nice long equation. So dot, 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 plus dot, dot, dot. And then I go, okay, plus minus, or I guess not plus minus, minus my shear is equal to 0. Because, of course, shear is going downwards. It'd be minus my shear. And let's just say that I get shear is equal to negative 25 kilonewtons. Okay, well, if I look up and I remember trusses, if I got a negative answer, what that means is the member's not in tension, it's actually in compression. And what I would do for trusses, so for trusses, I would write V, or I guess, let's not do V, let's do N, because there are no shear forces in a truss. So let's just go N, because this will apply the same thing. So for trusses, what I'd go is N is equal to 25 kilonewtons, and I'd put compression. And that's my final answer for trusses. For beams, however, things are a little different. So for a beam, I would put N is equal to, and this will kind of probably make you really confused, but then you'll be really happy. What I would put, if I get my normal force is negative 25 kilonewtons, for my N, I'm putting negative 25 kilonewtons. So this is very important. I'm going to switch to a yellow highlighter. I keep the negative because this sign convention is a standard. So what that means is if you get negative 25 kilonewtons, everybody will already know that the answer is in compression. Everybody will already know. And it's the same for shear. When it comes to shear, if it's negative shear, positive shear, we will know. You don't have to specify. You're just going to have to include the negative. And the reason why we keep the negative is mostly to do with moments. So if I have a beam right here, and I analyze 2 points on the beam. So let's say I analyze this point right here, and I analyze the point towards the end. And right here I get M is equal to a positive number, and on this side I get M is equal to a negative number. And most people, they say, okay, well, it's just, you got a positive moment, negative moments. What's the big deal? And it's how beams are designed. Because if I have a positive moment on this beam, what's going to happen is it's going to deflect like this. And if that's the case, we design it a certain way. But if the moment was negative in the middle, the beam's going to deflect like this. And now, when we're designing, those are two completely different cases. And they're very, very different and very, very important. So for us as designers, it's very important to know if the moment is positive or negative, which is why we have this very specific sign convention. It tells us exactly what we need to know for our design. And that's why we don't try and switch signs or anything. So if I get the moment is negative 10 kilonewtons, that's my answer, negative 10 kilonewtons. I don't try and, it's a moment, so it'd be kilonewton meters, but I don't try and change everything, which is what I'm trying to say. And I think that this example will hopefully kind of show that more in detail. So I'm going to put 2 lines, and we're going to start the example real quick. So if we look up to the example, as I said, it's very simple. And this week will always be the exact same example, and your lab will be the same thing too. Just determine the internal normal force, internal shear force, and internal moment at a point. And in this case, it says very clearly it wants it at point C. So what that means is sometime throughout this, in order to expose the internal forces, we're going to have to cut at point C. And I know that you guys are going to start getting flashbacks to the method of sections, and that's actually probably a good thing because the methodology is very, very similar. We can analyze either side of the beam, which we can do. So if we're looking at support conditions here, I can analyze only A. Because if I figure out the roller at A, so this support condition, well then all my unknowns on the left side are taken care of. And it's the same thing with B. If I want to analyze the right side, I can only find B, so I don't have to find A, because all my unknowns on the right side would now be known. So we only have to analyze one side, so we don't care. And what you'll find in this situation, it's always best to analyze the right side for this very specific situation. I'll show you why later. This is the one kind of thing that'll create problems for you guys, is a linear distributed load. I couldn't find my words for a second there. But before we begin, think about the method of sections. The first thing that we should do, draw a free body diagram and find the internal forces. So even though I only need one side, I'm going to solve them all anyway. It doesn't hurt, so why not? So I'm going to come down here, say, okay, I got a nice beam, which is going to go across, what is it, 6? We'll make it a little bit bigger, blow up the scale a little bit. Oh my gosh, and then that happens, of course. So we got a beam, we got we got a distributed load that kind of acts up and then comes down linearly. We know that the magnitude of this, if we look up, is 6 kilonewtons per meter. So we write 6 kilonewtons per meter. We know that this distributed load will create kind of a single force at a distance here. So I'm just going to put this here. I'm just going to call this F1 for now. I'm going to label my point C because that's going to be very important to us later. And finally, we know that we have a bunch of unknown support reactions. So over at B, I'm just going to put a single roller. So this is going to be BY. Over at A, we got a pin. So we're going to have a vertical and a horizontal force. And what you guys will find for this is there very rarely where we're going to have to deal with horizontal force. So this is going to be AX. And we got AY. And finally, we're going to have to throw in some dimensions. So the free body diagram, I'm going a little bit fast through. You guys are experts at this point. You guys know exactly what to do for free body diagrams. So this shouldn't be too bad. So we got 3 meters and 3 meters. And I'm just going to go up and check to make sure that I'm not losing my mind. 3 meters, roller at A. Oh, I guess this is A. So I did lose my mind a little bit. I know some of you in the video were probably yelling at me. Don't do that. Don't do that. You're going crazy. All right, so this will be BX, BY, and then finally we have AY. Perfect. So from there, we have, well, right now we have 4 unknowns, but we can get rid of one of them by solving for F1. So F1, since it's a triangle, we know it's going to be 1/2 of the base, which is 6 meters, times the height, which is also 6 kilonewtons per meter. And what we find with that is we get 18 kilonewtons. Perfect. All right, so that's not too bad. So coming down here, what we can do is we can take some of the moments at A or some of the moments at B. But actually before that, let's take some of the forces in X equals 0. And if we do that, what we find is that we have BX, and then we have plus, well, actually nothing. We look at the beam, all the forces are vertical. And this is very, very common in beams. So what we find is BX is equal to 0 kilonewtons. And what does that mean? Well, you guys will see later that that actually means that there's no normal forces on the beam. And you guys will actually come to see this quite a bit. So when it comes to normal forces on a beam, there's usually none. Because the whole point of beams is to resist forces that are perpendicular to the beam. So typically in these type of questions, what you guys would actually see is determine the internal shear force and bending moment. It's very, very rare of us to ask you for the normal force because there usually isn't any. The only time that there's typically a normal force is when the beam is rotated 90 degrees and becomes a column. But that's a little bit different. You have to treat things a little bit different, so we won't get into that at all. All right, so some of the force in X equals 0. we got Bx is 0. If we go sum of the moments, and we can take it anywhere at A or B, so let's go sum of the moments at A just for fun, just to switch things up, because we normally do it about the pin. What we find is we have the 18 kilonewtons, and that acts at a distance of 1/3 times the base, and we know that the base is 6, so 1/3 times 6. And if we look at the rotation this causes, it'll start causing a lot of C's, cause and clockwise, and it's going to create a clockwise rotation, so this is going to be negative. And then on the far side, we see that we have By, which acts at a distance of 6 meters. And we see that this is going to create a counterclockwise rotation, so this one will be positive. And we know that everything is going to equal 0. So what we can do is we can put By to the other side, and we can use our calculators. So we go 18 times 1/3 times 6, which is 36. Then we divide that by 6, and we get 6. So what we get is By is equal to 6 kilonewtons. And we know that this is a positive answer, so our assumed direction of up is correct. So again, I like to just kind of highlight these now, so when we look back, we can find them very, very easily. Coming down, we can find the last one through sum of the forces in y equals 0. Sum of the forces in y is equal to 0. Our equation here, we got Ay going up. We got 18 kilonewtons acting downwards. And finally, we got By, but we already know that By is equal to 6. So all that is equal to 0. You find that Ay is equal to, sorry, something in my throat, 12 kilonewtons upwards. And that's it. So those are our 3 kind of support reactions. And those are very, very typically what you guys are going to find first in these beams. Very, very rarely do you not find them. So from here, we can actually go into the fun stuff, which is finding those internal forces. So looking at our free body diagram, we want the internal forces at C. So we're going to cut the beam at C. We're going to make that cut, and then we can say, okay, well, we can analyze either the left side or the right side. But for this one, you want to analyze the right side. And the reason why is it has to do with the value of the linear distributed load. If we cut the beam, remember, we're only considering the stuff in that section. So if we consider the left side, we're going to have to deal with 6 kilonewtons, and we're going to have to deal with some unknown right there. If we analyze the right side, well, we still have to deal with that unknown, but instead of 6 kilonewtons per meter, we have 0. And 0 is always better than something that's not 0. So it's always better to pick the side with 0. So for this, what you would do is you would say, you're going to have to say very specifically, cut the beam at C. And then you're going to put free body diagram. So every time you make a cut, it's the same as trusses. We're going to have to make that free body diagram. And we're going to analyze the right side. Alright, so that's not a problem. So we come down. We know that we're cutting the beam. So we're going to only have kind of a little portion now. It's not that thick though. And on this beam, we can add everything that we know. So on the right side of the beam, we know that it's By and Bx. But Bx is non-existent, so we're not going to worry about that. So what we're going to have is By right here, and we know it's acting upwards in 6 kilonewtons. So 6 kilonewtons. We know that the distance from C to B right here is 3 meters. So this is why it's very important to include the distances to your cut. If you don't include the distances, we don't know the moment arms. And if we don't know the moment arms, then we can't use summation of the moments is 0. And we're going to actually really, really rely on that. So we're going to have to do that. We know that we got a distributed load coming down from this point up top. But remember, this point, we don't know it. If we look at our diagram right here, that point there is not 6, it's not 0, it's somewhere in between. And for this case, it's very, very obvious that it's going to be 3. But let's say that we're cutting the beam more at this side right here. And we're analyzing this point. Well, it's not right in the center, so it's kind of a little more tricky to determine what that is. So I'm going to show you guys the method to easily find out what that is. So right now we're just going to leave it as X. And we know that this distributed force will create a load on the beam right here. And this load will be dependent on x, so we can't figure it out quite yet. So we're just going to call it F2 for now. But now the one thing we're going to have to do is where we cut the beam, we're going to have to put in those those internal forces. So we cut the beam right down the center and we're analyzing the right side. So if we come up to our handy dandy diagram up here, what we did is we're analyzing the right side. So we're analyzing this case right here, where we got the beam on the right, internal forces on the left. So those sign conventions are exactly what we're going to use. So starting with shear, in this diagram, we have the shear going upwards. So I'm going to come down here. We know that our shear is going to go upwards like this. So that's our shear. And we know it's at point C, so I'm just going to label this VC. We go up here again. Our normal force will always be pointing away from our cut. So we come down here. We know our normal force is going to come out like this. So NC. And then finally we go up here and we go, okay, well, we have a moment. The arrow is always pointed towards the top of the beam. So we can come down here, draw our little arrow towards the top of the beam, and we can put MC. So this right here is perfect. Right now we have 5 unknowns, but we can solve for x and F2. So what we're going to end up is with 3 unknowns. And 3 unknowns, we got 3 equations. We can solve for everything. So this is really just a nice equilibrium problem. It's nothing actually too crazy. So from right here, the first thing we're going to need to find is x. And x, we need to define F2. And this is when we're going to use something called similar triangles. So what we're going to do is we're going to relate the slope of one triangle to a smaller triangle. So if I go all the way to the top, I see that if I look at this triangle as a whole, so if I'm looking from B all the way to the top and then down, then across, I should have done it just for the distributed load. I'm going to switch that. Oops. It's not what I wanted to do. I wanted to erase. Perfect. And then, so if I'm looking at this blue triangle right here, we see that it has a slope of rise over run, which is going to be rise of 6 over a distance of 6. So this triangle, for the big triangle, we know goes up by 6 over a distance of 6. And if we look over here, the slope of this smaller triangle, so the triangle that goes from here to this point, down, and then across, which is what we want because we want this point right here, x. Well, the rise is going to be x, so we don't know the rise. So we're going to have x over, but we know the run of this triangle. We know, excuse me, we know that the run is 3 meters. So coming down here, we're going to have x over 3. And we know that what this means, the rise over run, that's the slope. And the slope of this line doesn't change. So therefore, if we come down here, we know that 6 over 6 is actually going to be equal to x over 3. And we can solve that to find that x is equal to 3. And the meaning of this is kilonewtons per meter, the units. So now we know x. And now that we know x, we can say, okay, well, F2 is going to be the area under that triangle. So it's a triangle, so we're going to go 1/2 times the base, which is 3, times the height, which is 3. So all that is going to be equal to 4.5 kilonewtons. So now if we look at our free body diagram, we have 3 equations, we have 3 unknowns, we can solve for everything. And now this is where it gets really, really, really nice. So internal forces, they sound scary, but they're actually super nice when it comes to finding them at a point. Because if we look at our unknowns, one of them is perfectly in the x direction, one of them is perfectly in the y direction, and one of them is a moment. So what that means is it doesn't matter which equation I start with. It's impossible to have 2 unknowns in one equation. If I were to take some of the moments at the point at which I cut, so this point right here at point C, so if I take some of the moments at C is equal to 0, my shear and my normal force will not be in that equation because they act at that point. So my only unknown is MC. If I were to take summation of the forces and Y is equal to 0, well then NC wouldn't be in there because it's perfectly horizontal. And MC, the moment, won't be in there because it's a moment. It's not a concentrated load. So from here, we can pick actually whatever equation we want to start with. So let's just go down the list. We're going to go sum of the forces in X is equal to 0. Well, this one's very, very trivial because we see that we have NC, and it's acting left, so we're going to have negative NC, and that's it. So NC must be equal to 0. And this is very, very, very common for beams because there really isn't a horizontal load in beams. That, again, goes more to columns. So NC is equal to 0 kilonewtons. So we can highlight that real quick. Make this a little bit nicer. So we can come down here now and say, okay, well, going down the list, we got sum of the forces in Y must also be 0. So this is when we're going to have to start using the diagram a little bit more because we actually have unknowns. We have VC, and our VC is going up. So what we're going to have here to start is a positive VC because it's going up. We move on. We got F2 going downwards, and we know F2 is 4.5. So for this one, we're going to go minus 4.5. And finally, at the right-hand side, we got the 6 kilonewtons going upwards. So this is when we have to go plus 6, and that's it, equals 0. So solving for this, I get my VC is equal to, and we move the 6 to the other side, the 4.5, we get VC is equal to negative 2.50 kilonewtons. And this is where I said it'll start confusing you guys because typically when you guys have this negative answer, you guys have to change it. If it's a support reaction, you just change the arrow to go the other way. If it's a truss member, you say it's in compression. But this is what's nice about this is if you get a negative answer, you just leave it. I have my VC as negative 2.5. Perfect. That's the final answer. I don't have to change anything or do anything like that. So it's really, really nice. So we can finish off with our sum of the moments equals 0. So for sum of the moments, remember, you can take the moment at anywhere along the beam and you'll get the exact same answer. But what I recommend is always take the moment where you cut. Always take the moment where you cut. So in this case, I'm taking sum of the moments in C is equal to 0. And the reason why I do this is, let's say for fun that I took sum of the moments at A is equal to 0. You can do that perfectly fine. But what you're going to see is VC is going to create a moment. It's going to be VC times 3 meters. And let's say that you messed up your calculation for VC and you have the wrong value. Well, then your moment here is going to be wrong as well. But if I only take the moment at C, I don't rely on VC whatsoever. I only rely on the other stuff, which is more likely you got correct. So that's why I like to take the sum of the moments at C. So going along the beam, the first moment that we have is actually going to be MC, that concentrated moment, and we see it is clockwise. So we're going to have negative MC as our first one, negative MC. If we look up here, we got F2. So F2 we now know is 4.5. We know that it acts at a distance of 1/3 times that base, which is now 3 meters. So a lot of people put 6. Remember, our span of the beam has now changed to 3 meters since we cut half of it away. Okay, and then this is going to create clockwise rotation again. So this will also be negative. And finally, we got BY at the end, which we know is 6. And it acts at a distance of 3 meters. However, this one will start to create a counterclockwise rotation. So in this case, this side's going to be plus. And then everything must equal 0. And then I can solve for everything. I find that MC is going to be equal to 13.5 kilonewtons times meters. So I got a positive answer. I'm just going to leave it positive. I don't have to change anything at all. And that's what's really, really nice. I know it's kind of confusing for you guys at the start because I know that your heart's going to tell you, oh, something needs to change. But it doesn't need to change. You just leave whatever answer you get the same, and the reason why, again, of course, is because we used a very, very specific sign convention based on where we cut. So that concludes this example. We found the normal force, the shear force, and the bending moment at point C. And what you guys will see this week, that's it. And this is probably actually the hardest example this week because it's a linear distributed load. So if you guys can handle this one, you guys are good to go. Now, with that being said, of course, I have extra examples for you guys. So I'll do 2 more examples. But as you guys will see this week, there's not going to be a ton of examples because it's literally as easy as this. We don't have to change anything. There's no tricks. There's no anything like that. As long as you know this sign convention, you guys will be good to go. Now, why is this week so easy? It's because next week sucks. I'm going to be honest with you guys. Next week is one of the units I think students struggle with the most. Out of everything you guys learn in your entire Eng 130, I would say that next week's going to be your second worst week, with the following week being the worst week. But don't worry, I'll have videos on those, and we'll explain those when we get to them. So that concludes this video. Thank you guys all so much for listening, and I'll see you guys in the next tutorial.